Good afternoon, everyone. I'd like to welcome you to today's webinar, Explosion Risks and Mitigation Methods for Critical Process Equipment in the Biomass Facility. A special thanks to IEP Technologies, our sponsor today. I'm your moderator, Anna Simmet, editor of Biomass and Pellet Mill magazines. Our lineup of speakers today include Bob Zalash of Fire Protection Engineering, Mika Vanis of Addix and Oy, and Dave Grandda of IEP Technologies. Before we begin, a few housekeeping items. Following completion of our last presentation, there will be a Q&A session as time allows. If you have a question for all of our panelists or just one, you may submit them anytime. It is helpful if you specify who the question is for. Questions not answered during the webinar will be forwarded on to our panelists, who may answer them after the fact as time allows. A free recording of the webinar will be available within a couple of days following. It can be accessed on the Biomass magazine website under the Events tab. The slides themselves will not be available, so you can contact presenters directly to get copies of those. Contact information will be provided during the webinar. Moving along to a quick overview of today's webinar. Our speakers will discuss principles of combustible dust explosions, primary and secondary explosions, hazard assessment and ignition risks, spark detection and suppression, explosion protection strategies, and process vessels at risk. That about covers it, so let's get started and welcome our first speaker, Bob Zalash of Fire Protection Engineering. Bob, you may begin.
Thank you, Anna, and greetings, Biomassers. My assignment today is to describe dust explosion hazard analyses for biomass facilities. And I'm going to start by discussing the elements of a dust explosion, beginning with, of course, the combustible powder or dust that's often in a layer or pile form. When that layer or pile is disturbed so that a dust cloud is generated, then that produces the second element. And the photograph on the slide shows a dust cloud of, in this case, cornstarch that was on a table and was hit, so to speak, with a sudden opening of a compressed air line such that a dense cloud is formed, probably at a concentration above the minimum explosible concentration. And you can get a good idea of what's required in that, the density of the cloud that would be impossible to see through. It's dense enough to make it opaque. So the third element would be the air that's normally in the environment. And then if that suspended dust cloud at the right concentration encounters an ignition source, the fourth element, then we have this fireball that you see coming out of a vessel. And the fifth element, finally, is the confinement of the vessel, which produces the pressure that causes, in this case, a vented explosion. When does a burning dust cloud result in an explosion? The two factors are when the dust particles burn rapidly enough, and that depends on the dust particle size, and are sufficiently concentrated for the flame to propagate through the dust cloud. And then when and if the cloud is burning in an enclosure, be that process equipment or a surrounding building, the restraints from that explosion on the expansion of the gases is what causes the pressure to increase and hence produce the explosion pressure that's capable of causing the damage we want to avoid. In the case of biomass equipment, these suspended dust clouds may be present during routine operation in particle size reduction equipment, such as hammer mills and grinders, in conveying equipment that can be bucket elevators or screw conveyors, in storage bins during loading and unloading, in dust collectors during the in-feed to the collector and during the pulsing of the cartridges or bags, in the cyclone entrance and towards the more concentrated outflow towards the bottom of the cyclone, in pellet coolers due to the airflow, and in rotary drum and spray dryers. We would normally have suspended powder or dusts. Now, I'm going to turn to a few slides on ignition sources in this equipment, and I'm starting with tramp metal as a generic ignition source, and that would be consisting of unwanted metal in the form of screws, bolts, nails, washers, sockets, and a myriad of other small metal objects that can get onto the feed flow, as you well know, if you've operated a facility for any short period of time. And many of the consensus standards require either a magnet or some other metal removal device to prevent those small metal objects from getting into close quarters equipment where they can be lodged between what would otherwise be a moving element, and frictional heating and impact heating can occur, as shown in the next slide. So these are photographs of a powdered sugar hammer mill, where you can see that some tramp metal caused the burning of the sugar to produce soot deposits on the hammer, maybe some discoloring of the hammer themselves, and that produced an ignition that caused an explosion in the mill and propagated downstream of the mill itself. The next slide goes on to the kind of ignition sources that you might encounter in bucket elevators and various types of conveyors, and that's often due to different kind of frictional heating. In this case, possibly from misaligned belts or the buckets rubbing on the housing, as you can see, can occur from the witness marks to indicate the presence of that in some equipment. And towards the bottom of the slide, you see the other kind of common ignition source in this equipment, which is overheated bearings due to improper lubrication. And in particular, the ones on the bottom of the slide occurred on the discharge conveyor of a canola meal silo and started a fire in the silo, which led to other complications you'll see in a moment. The next, and these are some examples of elevator explosions and conveyor explosions that have occurred in some of these facilities, including on the right at a UK port facility where wood pellets were being loaded onto rail cars at the time of a conveyor explosion and silo fire. Here's some slide on the ignition that can occur in rotary drum dryers, and that's often from particulate accumulations or to the recycling of already dry fines. So in the example on the left of what you can see is a burned out drum dryer. In that case, the usual material inflow was temporarily halted because of some upstream equipment malfunction, but the fines, which already were drying, were recycled until finally they were overheated past the ignition temperature. The explosion did not occur in the dryer, but in some downstream equipment, pardon me, which I'll show you in another slide. On the right, you see a large rotary drum dryer in which an explosion has occurred to produce the damage to the outflow ducting in the lower right, and then even more damage at the front and inlet end that caused it to blow out hundreds of meters away and knock off some of the wall cladding on the building that you can see in the slide. The downstream equipment is also vulnerable to these same ignition sources, the sparks, embers, and burning fines from the mills and the dryers and the pelletizers. And this slide is just illustrative of the kind of interconnections of the equipment at pelletizing plants and maybe other biomass facilities, such that downstream coolers, pellet coolers, and dust collectors and bins can be the site of the actual explosion, even though the ignition source was generated upstream of that equipment. This slide illustrates some of the incidents that have occurred in silos and cyclones and the like. And I'll just mention the one in the photo in the center is of that same canola meal silo where they had the fire burning at the discharge and the bottom of the silo. The fire gradually propagated over a period of many weeks up to the rest of the silo. And unfortunately, and as that's burning, the incomplete combustion products are accumulating towards the top of the silo. There's usually a lack of air to create a flammable mixture, but when somebody makes a big hole in the silo to get access to the burning material, that allows the air, oxygen access, and the cutting equipment is the ignition source that created the explosion that caused that damage to the silo. This is some illustrations of dust clouds and ignition sources that can occur outside of equipment. So starting on the upper left, you see the corner delivery truck unloading station and the receiving pit below, where there's a dust cloud is formed from the unloading of the corn. On the lower left is a bag unloading and drum filling station for a mixing operation, where the dust cloud. Both of those are examples of open sources of combustible dust clouds. The diagrams in the center of the slide show the Nfpa 499 diagrams to designate where the Class 2, Division 1, and Division 2 areas would be surrounding an open dust cloud. You can see that the Division 1, or in the European case, Zone 0, area would extend 20 feet from the source, and then the Division 2 area would extend another 10 feet beyond that. On the right, you see examples of dust accumulations in an improperly sealed electrical outlet and on heavy dust accumulation on a large motor. The bottom of the slide points out that these division hazardous location, Class 2 locations, can occur with accumulations that doesn't only require a dust cloud, but can occur just due to excessive depths of accumulations indicated on the slide. This is an example of propagation of an explosion through interconnected equipment, such that the unfortunate casualties occur far from the site of the original explosion, which in this case was in a hammer mill. And you can see by the discolored metal that that explosion and fire traveled up the feed chute to the hammer mill, on further up to overhead conveyors, and traveled both upstream and downstream through those overhead conveyors, went all the way back to the receiving warehouse, where unfortunately one of the operators who was feeding material to the end feed conveyor was a casualty of the explosion that propagated and reached him. There was another casualty located at the baler far downstream of the initiation site. This is another example of explosion propagation through equipment. This plant was looking at downstream of the rotary drum dryer, where there was the fines were ignited. Those fines traveled up to a cyclone on the roof, and then the explosion occurred in the cyclone and then propagated through both the inlet and the outlet ducting to other equipment in the plant, and the duct breach in the building produced a secondary dust explosion in the building itself. In this case, there were not excessive accumulations, so there was only minor damage to the building, and luckily only very minor injury. This is a photograph of a wood pellet plant that was the subject of some interesting explosion propagation. Hot ember generated in the pelletizer traveled to the cooler in this plant and ignited fines in the cloud suspended dust in the cooler. That ember and dust was transported to a dust collector where the confinement was present that was required for the explosion. The dust collector was equipped with an undersized explosion vent, so there was some damage. The collector door and ducting were breached, but the explosion did not propagate back to the cooler because of effective explosion isolation in the duct. Another complication in this particular incident, you see the silos are located close to the wall of the building in which the vent duct from the dust collector was located, and the discharge of vented flame from the dust collector impinging on the silo wall caused a fire in the silo and required 14 hours of difficult firefighting to achieve extinguishment. Fortunately, in this case, there were no injuries at the plant or to the responding firefighters. Here's another example of explosion propagation in another, I believe, pellet plant where wood dust explosion in the production room propagated to the storage area and throughout the building. Fire spread throughout the building and eventually caused roof collapse. One firefighter was injured from a second explosion in that building. The Occupational Safety and Health Administration investigated these two incidents at those two pellet plants, and these are the outcome of those investigations. In the first incident, OSHA cited the pellet mill for serious violations of specific OSHA regulations and the Section 5A1 General Duty Clause, which requires employers to maintain a workplace free from recognized hazards. In this case, the fire and explosion hazards that became apparent in the aftermath of the incident and caused citations. And OSHA offered Nfpa combustible dust standards as examples of these recognized hazards and possible abatement measures that could have been used for these hazards. Unfortunately, we're not. In the second incident, OSHA found that the retention bin lacked spark detection, explosion suppression, fire and explosion isolation, and explosion venting devices. Conveyor systems carrying combustible wood products lack spark detection, fire suppression, or fire isolation devices. And you're going to hear a lot more about spark detection by the next speaker, and a lot more about explosion isolation devices from the third speaker. And OSHA cited the plant for 11 serious violations of workplace safety standards, and that plus the damage caused the plant were factors in the shutting down of this plant. This slide shows the relationship between the applicable Nfpa combustible dust standards for biomass facilities. So if we start on the left, the most general standard is the Nfpa 652 standard on the fundamentals of combustible dust. And then that references, depending on the type of facility, what we call industry standards or sometimes commodity standards. So in the case of wood pellets, that would be Nfpa 664, standard on the prevention of fires and explosions in wood processing and woodworking facilities. In the case of agricultural biomass, would be Nfpa 631 for prevention of fires and dust explosions in agricultural facilities. Those two standards in turn refer to Nfpa 654, which has guidance on spark detection and explosion isolation where it's required. And the standards also refer to Nfpa 69, which is the standard for explosion prevention systems and describes detailed requirements for explosion suppression systems, explosion isolation devices. Another pertinent standard is Nfpa 499, which is a guide and offers guidance on the classification of combustible dusts and the determination of corresponding hazardous locations. It's Class 2, DIB 1, and DIB 2 locations. Okay, now the actual dust explosion hazard analysis itself is now required per NFPA consensus standards for all facilities processing, storing combustible dust. The NFPA 652 standard, the fundamentals of combustible dust, specifies requirements and completion dates. Okay, the actual requirement says that the DHA shall evaluate the fire, deflagration, explosion hazards and provide recommendations to manage those hazards. It requires this to be done by a description of specific fire and deflagration scenarios, including the safeguards that are in place to prevent those scenarios and manage, control the damage from them, recommendations of additional safeguards that might be warranted. Okay, this slide is a little out to date. Unfortunately, we didn't get the updated slide in, but the current requirement in the latest edition of NFPA 652 is that these dust hazard analysis for all facilities, both new facilities and existing facilities, have to be completed no later than September 2020, and that there has to be significant progress towards those completions every year leading up to 2020. This slide was an old one with the previous from the previous edition of 652. Okay, since to reward you for being good, attentive biomassers, I've thrown in a little bonus slide to show you an interesting example of what can go wrong really unexpectedly, not necessarily involving combustible dust, but there's an explosion. What we're looking at is the remains of a Quonset hut building at a biodiesel plant. And one of the byproducts of a biodiesel production is glycerol. Glycerol has a melting point that's high enough that on a cold day you have to heat the tank to get the glycerol to flow. And on this particular cold day, the tank was overheated, and so flammable vapors of glycerol came out of the tank into the Quonset hut building. When an employee smelled those vapors, he tried to open the overhead door at the end of the building, but unfortunately the motor wasn't intrinsically safe, or the operation of that motor caused an explosion, which you can see blew off the end wall of the building and all the panels from the Quonset hut building, because they were not IEP explosion vent panels. So this is an illustration that beyond the NFPA requirements, there are other things that can go wrong that may warrant consideration of installation of ignition prevention and explosion protection systems. So at that point, I'll thank you for your attention and throw it back to you.
Thank you so much, Bob. A great job of getting us started today. Just a side note, a couple of questions have asked if presentations are available to download. You will need to contact presenters directly for that. Most will be providing their contact information during the presentation, so just write that down. And we will have a recording of the webinar available within a day or two on biomassmagazine.com. But all right, let's move on. Next up on the panel is Mika Vanis of Addix and Oy. Mika, I'm going to go ahead and turn it over to you.
Thanks, Anna, and thank you, Bob, from your presentation from explosion risks in the biomass industry. My presentation is going to handle spark detection and extinguishing systems and how to use them, minimizing those explosion risks. So I have listed here 7 facts from spark detection and extinguishing systems. They are especially designed for protecting production lines, not buildings, not facilities, but protection lines, and typically a small part of the production lines like conveyor chutes. They are the fastest fire detection and water extinguishing systems available. Typical reaction time of the detectors are only 1 millisecond. They are extremely sensitive fire detectors for ultraviolet to infrared radiation. They can detect even a small spark or hot particle through a wooden board. They use very little water for extinguishing, typically only 5 to 30 liters. With dedusting pipes, it's typically 5 liters, and with bigger conveyor chutes, sometimes up to 30 liters. There are also available alternative solutions like diverter gates or CO2 extinguishers. So state-of-art spark detection and extinguishing systems can do also much more than only detecting sparks. They detect ignition sources in their very early state. It can be even a 3 millimeter spark or hot particle very early before dust explosion or local fire will happen. And they are designed to minimize production stops or damage to production lines. So this is completely different to, for example, traditional sprinkler systems. Sprinkler systems start extinguishing fires when the fire is already relatively big and has already caused some damages to machines or buildings. At the bottom, we have 4 key components from the spark detection and extinguishing systems. On the left, we have spark detector. They are similar size to, for example, an apple, 80 millimeter diameter typically. Then we have water extinguishing, half meter length of the unit. They have integrated very high speed solenoid valve, very special type of water nozzle, flow switch monitoring water flow, and then ball valve position monitoring sensor for accidental closing. Pressure booster station is also a very important part of the system. It boosts water pressure high enough and makes sure that there is no water bubbles in the extinguishing water. And then control panel, of course, monitoring everything. It acts as a user interface, and it stores all the events to the memory. There are basically 2 different reasons to install spark detection and extinguishing system. The first one is to detect local fires in their early phase. They can be inside of the conveyor chute, inside of the hammer mill, bucket elevator, or belt conveyor. And we, at the very early state, spark detection system can react those fires and minimize the risks or damages to the production lines and making sure that they don't travel forward in the production line inside of the conveyor line, for example, because the extinguishing is very difficult to proceed there. The other reason why we have spark detection systems is that we use them to minimize risk for dust explosions. Explosions typically happens vessels like silos or dust collector pellet silos, and for that reason spark detection and extinguishing systems are installed to conveyor lines leading to those vessels. So the spark detection and extinguishing systems suppress all the ignition sources before they have access to those explosible vessels. Bob handled this topic already very well. Just short overview. Typical ignition sources, mechanical sparks because of physical impact. Any mechanical movement greater than 1 meter per second can create a mechanical visible spark, and it's typically yellow colored spark. Hot particle, it is even more dangerous because inertia level is much higher, and typically it happens to the friction. Third one is overheated machine. For example, dust fan. It's as you can see from the table, it can basically produce all different kind of ignition sources, mechanical sparks. If there is any piece of metal flying inside of the dust pipe and it hits wings of the fan, it can produce mechanical spark. If something is wrapping around the wings of the fan, it can produce friction heat and produce also hot particles. And sometimes those dedusting pipes or pneumatic transporting pipes, they can be blocked, and then air doesn't move forward, and then perimeter of the fan, temperature of the perimeter of the fan can increase higher than 200 Celsius degree and ignite local fire. And state-of-art spark detection and extinguishing systems, they have integrated overheat sensors that can measure also overheating from the machines. So Bob also handled this topic already. I think everybody knows explosion pentagon, what is needed for dust explosion. Here I have a short video showing how easily it can be done in real life. So we have a miniature dust collector. We have a small blower at the bottom. We have 50 grams wooden dust, and finally cigarette lighter as an ignition source. And once we put a ignition source inside of the vessel and we start this blower, immediately it will explode. Okay, it seems that this video is not working. Can you please, Anna, start the video? Oh, we have to go one slide backwards. Now this one. So very strong explosion happened even with 50 grams, only 50 grams of wooden dust. And we used aluminum tape to seal, to put those metal parts together. If they would be welded or if pop rivets or something there, the explosion would be significantly stronger. So the question is that, do we have those elements? And in biomass applications, typically the ignition source is often the last explosion element to present itself. So all the rest we typically have there. And very good starting point is to look for smaller than 0.5 millimeter dust particle size. It is kind of a rule of thumb. If you find that small particle size, dust particle size, it's a sign that it can explode. So here we have another video showing a solution, how spark detection and extinguishing systems, how quickly and how sensitively they can detect sparks and produce water spray inside of the conveying line. So we have here 300 Celsius degree hot particle. It's not a spark, it's hot particle, it's dark, it's not visible, you cannot see it by an eye. But spark detector is very sensitive and can react, also detect that kind of ignition sources. Airflow speed can be up to 60 meters, 200 kilometers per hour, and still a spark detector has time enough to detect it, and extinguishing system will suppress the ignition source. Only few liters of water to avoid damages to processes or production lines. And in case of multiple detection, software sparks, the control panel will interlock the production line. This is a mounting principle of a basic spark detection system. Here it's been installed to woodworking industry. So we have dust collector on the left, we have fan in the middle, and on the right we have a spark detection system. Number one, we have two detectors installed oppositely, and number two is water extinguisher. And typical distance between those two is 5 to 7 meters, depending on the speed of the air. We have local extinguishing controller, number three, very short sensor cables from detectors to extinguishing controller, and then it directly controls water extinguishing. Control panel number four is collecting all the information from the local extinguishing controllers and will save everything to the memory. Number six is fan controller, which will stop the fan in case of sulfur spark, and it can also measure overheat or temperature from the fans. So number seven is overheat sensing cable. And then we have pressure booster station number nine, water pump, water tank, and of course controller. For that it's number 8. Here we have other application, conveyor chute. What is the difference? Is a speed of the material. So with dedusting applications, it's 20 to 30 meters per second material flow speed, but here typically we have only 2 meters per second. Spark detectors, they are monitoring ignition sources, dropping down by gravity basis to the lower conveyor. Then local control unit activates water spray. Water is sprayed from nozzles in the chute, and extinguishing will stop automatically. If we detect more sparks, the extinguishing, of course, will continue. but everything works automatically. And in case of multiple detection, also conveyor line will be stopped. Sometimes those extinguishing systems have to be installed outdoor, and then they must be covered with thermal insulation and must be equipped with heat tracing system. Typical distance between detection and extinguishing is only 2 to 7 feet now because of lower material flow speed. Bucket elevator, quite similar to any other conveyor chute protection. At least outlet or discharge chute of the bucket elevator should be equipped with spark detection and extinguishing systems. Bucket elevator is rotating or moving with relatively high speed, and it can easily produce many different kind of ignition sources: friction, heat, hot particles, or mechanical sparks. Distance here from detection to extinguishing is typically 1 to 2 meters or up to 7 feet. Spark detection and extinguishing systems can also be used for monitoring dryers. Those wood chip dryers, wood chips travels on the dryer belt, and there are heated drying gas flowing through the material layer, and moist drying gas is vented to the atmosphere. And spark detectors are typically installed to those ducts leading to the sky. So if there is fire inside of the dryer, airflow will forward those ignition sources to the sky through the fan. And just before the fan, we have those detectors monitoring the duct, and we can give alarm to local PLC or factory automation system. Water extinguishing typically is not done because the volume here is very big. It's not typical for spark detection system to protect that big buildings. So spark detection system only gives an alarm, and then extinguishing can be done manually. Or sometimes spark detection system can also control dry sprinkler system. I think pellet manufacturing process is a very typical biomass application, and there are a lot of dangerous processes like drying, grinding, and pelletizing. Hammer mill, very dangerous component or machine or equipment, rotating very high speed and producing frequently mechanical sparks. It's good idea to have some distance before detection because hammer mill produces also low energy sparks. It's not good idea to spray water all the time. It's better to install detectors a little bit forward, some distance after hammer mill, and wait if those low energy sparks have already died. And if not, then it's the water extinguishing has to be started. We have bucket elevators many times there, so at least discharge chute of the elevators should be protected or equipped with spark detection systems. And then pellet mills, they use high temperature, typically 90 Celsius degree to 100, and if there is some failure inside of the mill, the temperature can immediately rise and it can ignite a local fire or even dust explosion. After pellet mills, there are typically other second elevator leading to pellet cooling system. And this pellet cooler is typical place where local fire accident happens. So spark detection system is typically installed the cooling pipe after cooler, and in case we detect sparks from that pipe, we know that there is a fire inside of the cooling system. On the right, you see a photo from diverter gate that can be used to redirect material flow from the production line in case water would cause problems with the pellets, because pellet can expand when it's in connection with water. So just before water extinguishing, we can redirect material flow out of the process line and proceed water extinguishing in waste gate. When choosing spark detection and extinguishing system to biomass applications, there are basically two very critical parameters for the detector, and the first one is viewing angle. The picture number 1 on the top left corner shows the conventional low-cost spark detection detector having 110-degree viewing angle. They work very well in dedusting pipes where concentration level is not that high. Picture number 2 describes what happens if we have very thick material flow between the detectors. So opposite detector cannot cover anymore those blind spots of the other detector. For that reason, it's important to have 180-degree viewing angle with biomass applications, because then the opposite detector doesn't need to cover blind spots of the other detector, because there is no blind spots. Picture number 3 shows that you see this vertical line in middle of the circle. So it's the point where the detector has to detect. So the left detector will cover the left half of the pipe, and the other detector will cover the other half of the pipe. So it means that detection distance is now halved compared to picture number 1. And when distance is halved, it means that we get 4 times better sensitivity level because of radiation theory. And finally, picture number 4 describes how well wide viewing angle detector works even if the material flow is thick. And in biomass applications, it's typically very thick pellet flow traveling in the middle between those two detectors. So it's important to have now wide viewing angle that blind spots wouldn't be there. Second very important parameter for the spark detector for biomass application is broad detection spectrum. At the top right, we have conventional spark detector measuring ultraviolet to visible radiation and also a little bit near infrared radiation. That kind of detectors, they can detect sparks through layers, but they cannot measure hot particles. It's an economic solution and very, very common solution. That kind of detectors are used a lot in dedusting systems. With biomass applications, it would be very important to being able to measure also hot particles. So the picture on the left, on the right middle shows different kind of detector. This is infrared detector, which measures only infrared wavelengths. as you can see at the top, this area is used to measure hot particles. But infrared radiation cannot go through layers. So we can measure hot particles, but not through layers. So optimum solution is to combine those two. So we have wide or broad detection spectrum, starting from visible light and going to infrared area. And then the detector can detect visible sparks, sparks through layers, and also hot particles emitting no daylight. They are totally dark particles, but still being capable of igniting dust explosion. So an ideal spark detector for biomass application is the detector having those two key parameters in the same device. So wide viewing angle, 180-degree viewing angle, and broad detection spectrum, that all kind of ignition sources that are possible to detect with optical sensor are covered. State-of-art spark detection and extinguishing systems, they support also other solutions, and they are integrated to the same system behind the same battery backup and behind the same user interface. The first one here is surface overheat detection cable. I mentioned it earlier. So the good solution on the left, measuring temperature from very long distance. It's measuring distance from the electrical motor. It's measuring temperature from the electrical motor, measuring temperature just above the ball bearing, and also measuring temperature from the perimeter of the fan. So if there is a channel blockage, the temperature on the perimeter of the fan will increase, and we can then detect it. If there is ball bearing failure, the area just above the ball bearing will be heated quickly. And if there is a overload for the electrical motor, the temperature of the motor will increase. On the right is a single point heat detector, which basically can measure perhaps a little bit ball bearing failures or overloading of the motor, but still it's not complete solution. Sometimes it's not possible to measure always inside of the process lines, but you need to come out of the process line and monitor a little bit kind of local limited area, still part of the production line, but outside. And for that purpose, there are available flame detectors, and they can be installed to the same spark detection and extinguishing systems. Reaction time of that kind of detectors are significantly longer than spark detectors, typically 1 second, 3 seconds, sometimes even 10 seconds. Still relatively high speed fire detectors, but totally different level to spark detectors. And now when the detector has more time to analyze fire, it's more immune to false alarms. So there are mathematic algorithms, and the sensor even knows what is burning there, if it's plastic or wood or paper. But spark detectors, they have to react within 1 millisecond, so they cannot make that kind of analysis. For that reason, spark detectors are typically used in enclosed area, in dark environment, and flame detectors are used in open areas. and they are monitoring machines or small part of the production line. Water mist extinguishing can be controlled by the flame detector. And for example, in this photo at the bottom, it's a very fine water mist extinguishing system is used to protecting hybrid burner. Then there are also available gas detectors when a biomass application is protected by spark detection systems. There are always some raw material storages that has to be monitored also, and there are available different kind of gas detectors monitoring many different gases to make sure that it's not only carbon monoxide, but it's really something is burning there. And it is important to have more than one, not only CO, but many different gases. And those are used for protecting silos or fuel storages, some kind of enclosed bigger areas. Typically not connected to any kind of a water or extinguishing system, but they provide only warning or alarms for users. Then there are some ancillary devices that can be controlled by the spark detection and extinguishing systems. Diverter gates, if water is prohibited, it's not possible to use water because of damages to material or production line, then diverter gate can be used. Slide gate is typically used together with CO2 extinguishers. So if before releasing CO2 gas, it's sometimes needed to stop airflow that gas wouldn't escape from the system. An abort gate is something what is especially used in USA, and it is used prior to returning air from dust collector back into the building. So in case there is multiple spark detection, this gate will be opened and it will direct flames and pressure wave to the safe zone, not back to the building. Short summary from my presentation. So spark detection and extinguishing systems, they can provide very early phase fire detection and extinguishing. They are designed for protecting production lines, low volumes of extinguishing water always, designed to minimize production stops, and detector solutions offer additional technologies such as gas and flame detection. Thank you.
Thank you, Mika. Before we move on, just a few quick words from our sponsor, IEP Technologies.
IEP Technologies, the name to trust for industrial explosion protection. IEP Technologies is the worldwide leading provider of industrial explosion protection systems and services. For over 60 years, we have provided protection solutions that can suppress, isolate, and vent combustible dust or vapor explosions in process industries. IEP Technologies can support biomass and ethanol operations through our facilities throughout the world, including in the US, Brazil, UK, Germany, Switzerland, France, Turkey, and China, designing and servicing systems with a dedicated team of application engineers, regional sales managers, and field engineers. The IEP Technologies process precise protection for every application. IP Technologies has more worldwide experience protecting a wider range of facilities against explosions than any other company. With well over 15,000 systems installed, we have developed a unique process to ensure the highest level of protection for our facility. The IP Technologies process includes material testing, an engineering site visit, system design, installation, commissioning, and maintenance. IP Technologies also offers on-site training programs for the proper operation and understanding of your explosion protection system. IP Technologies is a member of the Herberger Safety Solutions business segment, which provides comprehensive industrial safety solutions across a wide range of industries. Saving lives through explosion prevention and protection is the role of the IP Technologies and Gale brands at Herberger. IP Technologies is the systems and service specialist for the entire range of explosion protection solutions in dust and gas applications, which now includes the Texon range of spark detection and extinguishing solutions. Gale brings decades of experience in mitigating fire and explosion risks from electrostatic spark discharges. These brands complement the flameless venting expertise that Herberger has accumulated over the decades, as well as their expertise in industrial engine and generator protection. You can't afford to let an explosion threaten your critical facility. Let us work with you to keep an explosion from impacting your bottom line. Call IP Technologies today.
Thank you. All right, moving on to our final presentation of the webinar. It's Dave Grandda of IEP Technologies. Dave, I'm going to turn it over to you.
Very good. Thank you, Anna. Tammy, it looks like you'll have to advance my slides for me. Okay, good afternoon, everyone. This next section, we're going to talk about explosion protection measures that can be used at biomass facilities. Bob had covered in the earlier section the various Nfpa codes that are applicable to biomass facilities. These include Nfpa 654, which is the combustible particulate solids standard. It includes Nfpa 664, which is for wood processing facilities. Nfpa 652, which is a relatively new standard that handles just the general fundamentals of combustible dust handling. It also includes standards regarding how to implement some of the explosion protection measures that are to be used at these facilities, including Nfpa 68, which is the venting of deflagrations, as well as Nfpa 69, which is for explosion prevention systems. Nfpa 69 covers explosion suppression, covers spark detection, it covers explosion isolation, and there's some other explosion protection and prevention techniques such as inerting and containment that are typically not applicable to the biomass industries. Explosion venting is the first technique that we're going to cover. And explosion venting is by far and away the most common means to protect a vessel from an explosion. Explosion vents are an opening in a process through which combustion-generated gases can flow to the outside and then expand. The whole purpose for an explosion vent is to minimize the overpressure to a point where you don't have rupture or or even deformation of the process vessel. Explosion vents come in a lot of different shapes and sizes. Some are round, some are rectangular, some are square, or some that are domed, some are flat. Some that are open through a rupture style, such as the type that we're showing on this particular slide, where there's score marks and they opened at a predetermined pressure level. Others are held on by magnetic latches. Some have shear bolts or plastic bolts that let loose. There are some that are even gravity type vents. In all cases, these vents are designed so that they would open up at a predetermined set point. When trying to determine whether or not explosion venting is going to be the suitable explosion protection method for an application, first thing that one would want to look at is, can I throw that fireball to a safe area? Can we direct this fireball to an area where there's not going to be personnel, there's not going to be another building or other process equipment that could result in a fire or even a secondary explosion? That explosion fireball can be thrown quite some distance. You'll see from this demonstration, from this video, both the release of the fireball and actually the propagation from the source vessel back upstream. And we'll talk about that propagation in a few slides. But certainly the first consideration should be when looking at explosion venting is, can we throw this fireball to an area that we just aren't going to cause any life safety issues or any further property damage issues? The size of that fireball can be more than 7 times the volume of the vessel, and the ejection distances can exceed 50 feet. Remember doing a calculation some time back where in this particular application, the calculated fireball distance was 132 feet for this application. So it's really important that when you look at the explosion venting, even for an outside vessel, make sure that that fireball is not directed at a parking lot, at a sidewalk, at another process vessel. This graph is, I want to show you what actually happens during a vented explosion. If you can see my cursor moving, the point where the vent opens up is called the static pressure that the vent opens up, or P-stat. It does take a finite amount of time for that vent to fully open. And during that period of time, that pressure will continue to rise until you get the full effects of the vent opening. And at that point where the pressure starts to degrade, it's called the P-red, or reduced pressure after venting. The P-red is the value that you should be looking at when you're trying to determine how much vent area is needed for a particular application. That P-red must always be below the strength of the vessel. Must always be. As a matter of fact, Nfpa 68 recommends that it should not exceed 2/3 of the burst pressure of the vessel. The point of this slide is that if you have a vent that's designed to open up at 1.5 psi, and you have a vessel that's designed to handle 1.5 psi, it's not going to work. The vessel will likely tear apart if you get a good homogeneous dust-air mix within that vessel. It's the P-red that we're really looking at, keeping that P-red below the vessel strength. Now, Nfpa 68 is the standard that's used for determining the sizing for the explosion vent. One thing that NFPA does allow, it does allow the use of explosion vents for inside vessels. However, it does say that these vents must be directed to the outside. You cannot have a vent like we show in this picture that's directed inside the facility. You've actually created a much more dangerous situation than if you had a completely enclosed vessel, because now you've created a weakened spot that's going to eject flame into the building, stir up dust, create a secondary dust cloud that then will be ignited, and a secondary explosion that will likely destroy the the occupancy of where this vessel is being mounted. So it's just important to note. Yet an inside vessel with explosion vents must be ducted to the outside. There are some calculations in Nfpa that advise you what the penalty, if you will, is in either vent oversizing or beefing up your vessel to account for the vent duct that must be installed. Finally, on explosion venting, keep in mind that all a vent does is it relieves pressure. So it will not put out the fire that's going on, the subsequent combustion that's going on inside the vessel. So that must be accounted for. It will not stop any flame propagation that's going upstream, downstream, or through the exhaust duct if that exhaust is being recirculated. There is a second means of explosion venting that is sometimes used for inside vessels, and it's called a flameless explosion vent. A flameless explosion vent is an opening with a flame arrestor around it, through which the combustion generated dust and overpressure would travel, and that flame arrestor basically drops that temperature down to about 90 degrees C. So there's a little bit of a typo here where it says 900. In reality, it's 90 degrees C, something under 200 degrees F. As these hot gases then are emitted to the outside perimeter of these flameless vents. So you'll see on these two vessels, you'll see a couple of mounted flameless vents, as you'll see on the lower vessels. Now, the way one particular type of flameless vent works, the spring-loaded style vent, the type we saw in the previous photograph. So right here would be the actual vent itself. There's a spring positioned just up above it. So during normal operations, the spring holds the vent closed. When you have an explosion, the pressure from that explosion pushes the plate up, compresses the spring, and then the hot gases and flame will travel through this sintered metal, which acts as a heat sink, absorbing the heat, so that all that's released is hot air and some dust to the outside, but no flame. Flameless explosion vents do have their place. They're typically good for smaller volume applications, for stronger vessels with a little bit higher P-red. Flameless explosion vents, even though they're not emitting flame, they still should have a safe zone around them, because when you're in that 180 degrees to 200 degrees F area, someone could be scalded if they get hit by that sort of a temperature. So you still would want to have an exclusion zone around the perimeter of flameless explosion vents. So they certainly do have their place, and they can be a very, very effective explosion protection means. The next explosion protection means that we'll cover would be explosion suppression systems. So explosion suppression systems are systems that detect an explosion at early stages and then very, very quickly disperse a suppressant agent to put out that explosion while the fireball is still relatively small. If you recall before, we talked about the 5 elements needed for an explosion. That would be the oxygen, that would be our confined vessel, that would be an ignition source, that would be the dust, and that dust would have to be the combustible fuel or the dust, and that dust would be in dispersion. So what we're going to show now is just an animation of an explosion suppression within a confined vessel. The red device that we see here would be a pressure style detector. We show an extinguisher on the side of this vessel, as well as an extinguisher on the inlet duct, and I'll cover that in just a second. Above, you'll see the kind of a time lapse of this event. You can see the pressure that's emanating from the explosion. That pressure travels at the speed of sound, or about 1,100 feet per second, while the fireball itself is only growing at something in the range of 3 to 10 meters per second, to something 10 to 35 feet per second. So that pressure wave that's being traveled from the initial deflagration is being picked up by the pressure sensor through a control panel, and that triggers the suppression system to activate. Explosion suppression systems are similar to a fire suppression system in that it has three main components. We have detection, control, and extinguishers. The systems do operate much quicker, however. Detection is typically done using pressure-activated detectors. At times we might use infrared detectors or even ultraviolet detectors. But the most common for combustible dust, which we would find at a biomass type facility, would be a pressure-style detector. We're going to show a video now of the extinguisher, just so you can get a sense of how fast these extinguishers must discharge in order to put out that deflagration. That agent velocity is about 250 feet per second. And it has to be that fast for that agent front to get to that flame front within that milliseconds that are required in order to get effective suppression before the overpressure gets to the point where it ruptures the vessel. In order to design an explosion suppression system, there's some basic information that must be obtained. Knowing the type of material it is and its explosivity characteristics, which I'll touch on in just a slide or two. The process conditions, operating pressure, operating temperature are important to understand. The vessel volume, even the L over D of the vessel, will affect the way the geometry of which the explosion itself is going to grow within the vessel. Certainly the vessel strength is very important, because when you design an explosion suppression system, let's try to stay below that vessel strength so we don't have a ruptured vessel even during a suppressed event. Typically, systems nowadays are designed using computer modeling. Some of the more archaic methods, I guess, of designing an explosion suppression that were used years ago would use a simple volume versus concentration calculation. And we know from many tests now that there's a lot more parameters that must be taken into account when you design an explosion suppression system, including how far you have to throw the agent, what the detection set point is going to be, even whether extinguisher is going to be mounted vertically or horizontally. So all this information is put into a computer model to determine an explosion suppression system that's correct for a specific application. Whether you're using venting, flameless venting, or explosion suppression, you still have an issue in that vessels are being fed and they're typically discharging, and oftentimes there's dust lines. And through these openings, flame propagation can occur. Does it make a lot of sense to have a dust collector that's outside, that has explosion vents properly employed, and have that vent work properly? The vessel itself is saved, but an explosion will then propagate back through the inlet duct back into the plant, picking up off of various vessels, causing secondary explosions. Basically, the dust collector is saved, but you lose the inside of the plant. Makes no sense. It's really critical, and maybe one of the most overlooked part of an explosion protection philosophy within a facility is to have proper explosion isolation on these propagation points. Most of the Nfpa documents regarding combustible dust and wood processing in biomass facilities, really any combustible dust application, do mandate the use of explosion isolation. There's a couple of different types of explosion isolation that can be used. The first one is known as active explosion isolation. The second is passive explosion isolation. An active explosion isolation method would be the use of the same style of extinguishers that might be used for suppression, but instead of being positioned on the vessels or in conjunction with being used as suppression on vessels, they would be located on interconnecting ducts, pipes, chutes, and so forth to create a chemical barrier to stop the flame from moving from one vessel to another. Another means of active explosion isolation would be the use of high-speed knife gate valves. In the center and on the right, you'll see examples of these high-speed knife gate valves. although they are very, very easy to understand how they can create a mechanical barrier to stop an explosion, in reality, they're seldom used for biomass facilities simply because of the cost. They're very, very expensive, so they're typically more likely to be used on really high value products, such as what you'd find in a pharmaceutical facility. So chemical isolation would be the most common means of active explosion isolation at biomass facilities. Passive explosion isolation is becoming increasingly more recognized and used in, especially in dust application, where you're picking up dust from vessels and traveling to some sort of a dust collection system, whether it be a cyclone or a dust collector. These passive isolation valves basically work on the principle that the airflow going through the valve would open up an internal flap inside the passive isolation valve, and then that dust would pass through the valve onto the vessel. When an explosion occurs, recalling that we have a pressure traveling faster than the flame, the pressure front would cause the internal flap to close so that when the fireball reached that flap, it then would be mechanically stopped. Because these valves are often less expensive than a chemical barrier, they're increasingly more commonly used. We're going to run a quick video just giving you an animation of how the valve actually works, both in normal speed and then in slow motion. So here we see the dust-laden air travel through the flap valve that opens up the flap. When the explosion occurs, the pressure front is going to close that flap so that by the time the fireball gets there, it's going up against a closed gate. There is a section in Nfpa 69 that specifically handles the minimum prescriptive requirements for the design and use of flap-style passive isolation valves. Because we have a number of different choices when we're looking at explosion protection, some of the things that must be taken into consideration for what type of explosion protection should be used are listed here. Basically, if the vessel can be safely vented, then venting is often going to be your least expensive alternative. But keep in mind that you must take into account that explosion isolation threat, propagation threat and isolation protection measure. Mentioned before that the explosivity characteristics of the dust is going to have a big factor regardless of what type of explosion protection is being used. Some of the most common characteristics that would be looked at by companies that design explosion venting, explosion suppression, explosion isolation systems would be the maximum pressure developed during an explosion, which is known as the Pmax, and an explosivity indexing based on the rate of pressure development, which is the KST. The KST basically tells those of us that are designing explosion prevention measures how fast do we have to react to an explosion. For those of you that have plants that have combustible dust, whether that explosion pressure is going to grow in 50 milliseconds or 500 milliseconds, doesn't matter. You're not going to be able to react fast enough if you don't have the proper protection measure in place. So it's really important that you keep that in mind. The KST just tells us how much time we have to react. It really doesn't tell us how much pressure you're going to generate during an explosion or whether or not you have an explosion threat, unless your KST value is really low, in the range of single digits. We're going to quickly cover some of the most common risks areas within a process area for a biomass facility. And one of the really most common explosion risks that we're going to find in any sort of an organic dust application would be a dust collector, a bag house, filter receiver, air material separator. These are vessels that are used for separating particulate from an airstream. And the reason that these are probably one of the most common threats that we find within the facilities is because the finest dust in the entire facility ends up inside these vessels. And that's bad for two reasons. The finer the dust, the easier it is to ignite, very similar to kindling versus a log. Also, the finer the dust, the faster it's going to burn. So you're going to have the higher rate of pressure development. Again, similar to kindling versus a log. The finer it is, the faster it burns, the hotter it burns, the easier it is to ignite. It's the same thing with dust. One other big threat with dust collectors is that oftentimes at your facilities you'll find that these dust collectors may serve multiple vessels. You may have a dust pickup from multiple vessels. So if you have an explosion within a dust collection device, the propagation threat now is spread to different areas of the plant. So that makes the threat even that much more serious to address. Other types of air materials separators common for biomass facilities would be cyclones. And cyclones present some of the same types of risks that we would see in a dust collector. Mills, grinders, pulverizers are some of the most common mechanical ignition threats that we'll find within the facility. Material and product conveying. In and of themselves, oftentimes the ignition source isn't going to start within mechanical conveying unless you have a bearing that's gone bad. But let's say you have a belt conveyor. Sometimes that ignition source may be conveyed into that conveyor, and at the pickup points and the load points and the discharge points, you have dust clouds in which an explosion can occur. Storage vessels are very, very common explosion risks because all the material eventually is going to end up in a storage hopper. What we're looking at here is these are actually wood pellet storage silos with explosion vents positioned on the upper section. Just to kind of summarize what we've covered, when we're looking at explosion prevention at a biomass facility, the first thing you really want to do is do a good process hazard evaluation. And we want to look at what the normal, abnormal, and upset conditions are that can occur within each part of the process. We want to look at how combustible the material is. How easily is it to ignite? Is it susceptible to electrostatic discharge from an ignition source standpoint? We want to look at some means to control ignition sources. Spark detection and suppression is one of those means. Having proper bonding and grounding is very important, especially if you have fine, dry wood dust. Having the proper electrical classification for your instruments within these areas so that you're not using general purpose electrical devices in an area that really is a class 2 Div 1 or so rated area. Just making sure you have good control of frictional or impact sparks. Proper housekeeping is so critical. Primary explosions within a vessel will take out the vessel, but if that primary explosion gets into the room and you have improper housekeeping and dust clouds are released, that causes a secondary explosion that will take out the building. Having good operator hazard training and awareness, making sure that they understand the threats that are around them so that they work in a proper and safe manner. Those are all real important so that during normal operations, explosion risks can be minimized. Since explosion risks can't be completely eliminated, having proper explosion protection for vessels that are at risk is critical, as is having proper explosion isolation to stop that flame propagation potential that could occur. That's the conclusion of my presentation. Anna, I'll turn it back over to you.
Thanks, Dave. That rounded out the panel really nicely. We're running right past 2:30, so unfortunately we don't have time for any live questions, but we will be forwarding all questions asked during the webinar to our panelists so they can reach out to you directly with answers. And a recording of the webinar will be available soon at biomassmagazine.com. For slides, you will need to contact presenters directly. Those of you who tuned in today are eligible for an exclusive $100 discount to the International Biomass Conference and Expo being held March 18th through 20th in Savannah, Georgia. Just call 866-746-8385 and mention code OFF100. And finally, be sure to check out these upcoming events that you might be interested in. Thanks again to our speakers, our sponsor, IEP Technologies, and our webinar attendees. Watch for a replay of this webinar at biomassmagazine.com in the near future. Have a great day.